So picture this. You're watching an incredibly sophisticated AI, a system that's been trained on basically the entire sum of human knowledge, and it's trying to rebook a canceled multi-city flight for you.
Right, which sounds like something it should easily handle.
Exactly. It's got all your details, it's connected to the airline system, and it's moving along totally fine. But then the airline's website changes a button from continue to next. Just a tiny cosmetic change.
Oh, yeah. We see this all the time.
And the AI it completely freezes. Or worse, it sort of panics and starts hallucinating an entirely different itinerary to a city you never even planned to visit, stubbornly trying to book a hotel you absolutely don't need.
Yeah, it's just completely derailed by one word.
It's the ultimate modern paradox, you know? We have
Sure.
these systems with near infinite data, but the very moment they face a single unexpected hurdle, they exhibit zero common sense. Welcome to today's deep dive, everyone.
Thanks for having me. And yeah, the brittleness of these systems, it is arguably the single biggest bottleneck in automation today.
It really is.
We apply this label, like we call them intelligent agents, and assume they possess this foundational awareness of their environment. But in reality, when they encounter a state they haven't seen before, they just lack the underlying logic to recover. They honestly don't know how to navigate failure.
Right. And if you listening have ever tried to build a reliable workflow using an AI agent like trying to automate your email or your research, you know that brittleness is expensive and it's just infuriating.
Extremely frustrating.
So our mission for this deep dive is to fundamentally demystify why these agents fail so spectacularly at multi-step tasks, and we're going to look at a brilliant new method to fix them.
Which is really exciting stuff.
It is. We're pulling apart a state-of-the-art foundational Gen AI paper. This is from researchers at Johns Hopkins University. It's titled Agentic-DPO, From Imitation to Agentic Policy Optimization on Expert Trajectories.
It's a bit of a mouthful.
Yeah.
But the core premise here is shifting how we actually teach these models.
Yeah.
Instead of forcing an AI to blindly memorize a perfect script written by a human, this research proposes a highly efficient way to force the AI to confront and really learn from its own hypothetical mistakes.
Without ever needing to practice in a live, expensive environment.
Exactly. Completely offline.
So if you are a developer, maybe an investor, or just someone trying to figure out why your digital assistant is so frustratingly stubborn, you need to understand this shift. But before we get to the Johns Hopkins solution, we have to look at the flaw in the foundation.
The way we do things right now.
Right. Okay, let's unpack this. The current low-cost standard for training large language model agents is something called supervised fine-tuning, or SFT.
Right, SFT. And SFT is essentially the workhorse of the current AI industry.
Because it's cheap, right?
Exactly. It is cheap and straightforward to implement. The process involves gathering a massive data set of what we call expert trajectories.
And a trajectory is basically a log.
Yeah, you can think of a trajectory as a complete log of a task being executed perfectly, step by step. Usually by a human expert or, a massive, expensive AI model like GPT-4.
Okay, got it.
So you take those perfect logs, you feed them into a smaller, cheaper model, which we call the student model, and you just train it to imitate that sequence.
So you're basically just feeding it the answer key, token by token.
Token by token, predicting the very next word in the sequence. And that's the issue. SFT treats complex, multi-turn agent behavior as if it were just ordinary text generation.
Like it's writing an essay or a poem.
Right. It looks at the string of words the expert used and adjusts the model's internal weights to make it more likely to produce that exact string. But the problem is that an agent operating in an environment isn't just generating text. It is making state-conditioned decisions.
State-conditioned decisions, meaning it has to look at what's happening right now.
Exactly. At step 5 of booking a flight, the state includes the user's prompt, the history of the conversation, and the current screen of the airline website. The model has to look at that state and actually decide, do I use a search tool? Do I ask the user for a passport number?
It has to make a choice.
Yes. But SFT completely ignores the decision-making process. It doesn't teach the model how to choose the right action when faced with a slightly different state. It just demands blind imitation.
Okay, I think I get it. It's like trying to learn how to play chess by just memorizing a written list of winning moves from a grandmaster.
That is a perfect analogy.
Right, like you might memorize that moving your pawn to e4 is a great opening, but you aren't learning why it's a great opening.
You don't understand the board control.
Exactly. And more importantly, When your opponent makes a move on, say, turn 12 that isn't written down in your memorized list, you are completely lost. You haven't actually learned the underlying policy of the game.
Right, you've just cloned the text of a winning game.
Yeah. And when the AI inevitably makes a slight mistake like maybe parsing a web page incorrectly, it enters a board state it hasn't memorized.
Which leaves it with literally zero recovery mechanism. Under supervised fine-tuning, the training signal is entirely positive.
Just a pat on the back for getting it right.
Right. The model is shown the perfect path, but it is never shown what a mistake looks like at that specific moment. It doesn't know why the expert didn't choose an alternative action.
Because it's never been punished for it.
Exactly. Because it has never been mathematically penalized for the mistakes it naturally wants to make, it has no internal compass to guide it back to the correct path when it wanders off.
Man, that makes so much sense. So the obvious next thought is just stop making it memorize lists and let it actually play the game, right?
They get some real experience.
Yeah. Put the AI in a live environment, let it click around on the internet, query live databases, make mistakes, and learn from experience.
Yeah, and to be fair, the industry certainly tries to do that. That approach relies on reinforcement learning, or RL.
Okay, RL.
A popular method right now is called online GRPO. That stands for Group Relative Policy Optimization. In GRPO, you give the model a prompt and have it generate a whole group of different attempts at the task in a live environment.
Like trying different strategies all at once.
Yeah. We call these environment rollouts. Then, a separate reward system grades all those different attempts, and the model updates its policy to favor the actions that scored highest relative to the rest of the group.
Okay, well, that sounds incredibly thorough. It's actually learning from trial and error. But I'm guessing the keyword you used earlier, live environment, is the deal breaker here.
It absolutely is. The computational cost is staggering. Think about what an environment rollout actually requires.
It has to actually do the stuff.
Right. The AI has to interact with real software. You have to spin up simulated web browsers. You have to manage API rate limits for databases and execute code safely.
Which takes time and server power.
A massive amount of both.
Mm-hmm.
Then you have to build complex custom reward models to figure out if the AI's action actually achieved the goal. Doing that for a whole group of trajectories for every single step of training requires massive amounts of compute.
So we're kind of stuck between a rock and a hard place. We want the deep strategic understanding of reinforcement learning, but we are stuck with the cheap offline convenience of supervised fine-tuning.
Exactly. We need a bridge between the two.
And that brings us to the Johns Hopkins researchers' solution, Agentic-DPO.
And what's fascinating here is how they bypass the need for a live environment entirely. So DPO stands for Direct Preference Optimization.
Okay.
Historically, if you wanted to train an AI on preferences, you had to train a second separate AI to act as a judge, which is, well, it's complex and unstable.
Two AIs arguing with each other.
Right. DPO revolutionized things by mapping human preferences directly into the language model's mathematical objective. You give the model a preferred response and a rejected response.
A good one and a bad one.
Yes. The math adjusts the internal weights to pull the model's probability distribution toward the good response, while explicitly pushing it away from the bad one.
Got it.
The agentic part of Agentic-DPO means they tailored this specific math to an agent taking actions.
So right, they're doing this entirely offline, like no spinning up browsers, no live APIs.
Zero online rollouts. They take the exact same expert trajectories used in SFT, those perfect step-by-step logs we talked about.
The answer keys.
Right. Let's say we are looking at step 4 of a task. The system knows the exact action the expert took in that state. That becomes the preferred action.
Makes sense.
Then the system essentially pauses the tape, looks at the current student model being trained, and asks it to generate a one-step action based on that exact same history.
Oh, wow. So it's testing the student's instincts. It wants to see what the student would naturally do in that specific scenario.
Yes, exactly. The student model generates a few plausible actions. The system identifies a plausible wrong action, labels it as the rejected negative, and applies the DPO preference objective.
Pushing it away from the mistake.
It mathematically forces the model to increase the probability of the expert's decision while simultaneously squashing the probability of the student's natural mistake.
Okay. I have to push back on this because there seems to be a massive logical hole here.
Look here.
If this entire process is offline and the AI isn't actually clicking buttons or running code to see what happens, how can the system definitively know that the AI's generated action is a mistake?
Ah.
Like, what if the student model comes up with a perfectly valid alternative way to solve the step that just happens to look different than the expert's way? You'd be penalizing the AI for being creative.
That is the defining hurdle of offline training. And it's a great catch. The researchers addressed it with a mechanism they call a hardest different action rule.
Hardest different action.
Right. They recognized that language models can express the exact same underlying intent in wildly different formats. So, before the system chooses a negative action to penalize, it filters the students' generated responses.
How does it filter them?
It looks for actions that are fundamentally equivalent to the expert's decision. If the expert chose to search a database using an email address, and the student model also searched the database with the email address, but maybe swapped the order of the arguments in the code.
The system recognizes that the latent decision-like, the core intent, is actually identical.
Exactly. It throws that response out. It doesn't penalize it.
So it separates the intent from the syntax.
It has to. Once it filters out the equivalent actions, it is left with a pool of candidate actions that represent genuinely different latent decisions, actual deviations from the expert's strategy.
Real mistakes.
Real mistakes. From that pool, the system selects the action that the student model assigned the highest probability to.
Oh, it finds the worst habit the student is most confident about.
Yes, it isolates the exact wrong turn the student is most likely to make at that specific state and uses that as the rejected example.
That is so smart.
The DPO gradient explicitly updates the model weights to suppress that specific bad assumption. And because it only samples one single step at a time, locally, it completely avoids the computational nightmare of running full trajectories in a live environment.
That is incredibly elegant. But I imagine applying preference optimization to text-based AI creates a secondary massive technical headache.
It definitely does.
Because these language models don't output abstract thoughts, right? They output text strings. And an action written in text mixes up two entirely different things.
The intent and the format.
Right. There is the latent policy decision, which is what you actually want the AI to do, like looking up a customer. And then there is the schema, which is the specific formatting, the brackets, the syntax used to write that action down.
Yeah, and this entanglement of decision and formatting is a known bottleneck. Let's say the expert action is to query a database, and the student's highly probable mistake is to try and answer the user directly without looking up the information.
Two totally different choices.
Totally different. In text, those two actions look completely different, not just in their intent, but in their punctuation. If you apply the DPO math naively to those two text strings, the gradient gets confused.
How so?
Well, the AI might notice that the rejected action didn't use curly brackets, while the preferred action did. So the model starts optimizing for always use curly brackets, rather than optimizing for always query the database.
Here's where it gets really interesting. It's like teaching a student complex calculus.
Okay.
You want them to learn the actual formula. That's the latent decision. But if every single correct answer in the textbook happens to be printed in a specific blue font and the wrong answers are in red, the student might just start associating blue font with correct.
So they just game the system.
Right. They aren't learning the math, they are just learning a style preference. We need the AI to focus strictly on the calculus, regardless of the font.
That's spot on. The AI will always look for the easiest mathematical shortcut, and memorizing syntax is easier than learning policy.
So how do we fix it?
To force the model to focus on the latent decision, the Johns Hopkins researchers had to stabilize the training process. They introduced two critical mechanisms. The first is called the SFT anchor.
The SFT anchor. Because before you can teach the AI nuanced preferences, you have to ensure it actually remembers how to speak the language in the first place.
Exactly. The DPO process is so aggressive at pushing away from negative examples that the model can actually unlearn basic grammar.
Wait, really? It just breaks.
It literally forgets how to format a basic tool call because the weights get distorted by the penalty gradients. The researchers noted that without an anchor, the model hits a 100% parser rejection floor.
Meaning every single output is just garbage text that the system can't even read?
Yep. The SFT anchor maintains a baseline of supervised fine-tuning running concurrently with the preference optimization. It constantly pulls the model back to baseline valid syntax.
Oh, that makes sense. It keeps the student from getting so panicked about making a mistake that they forget how to hold the pencil. The anchor keeps them grounded. But the second stabilizer, this is really the secret sauce of the whole paper, isn't it? Policy-preserving augmentation, or PPA.
PPA is how they break the association between your blue font and the correct answer. The goal of PPA is to render the exact same latent expert decision under multiple different schemas, forcing the model to realize that the formatting doesn't actually matter.
Okay, so it scrambles the fonts, so to speak.
Right. The researchers deployed two main families of PPA. The first is action rendering rewrites, which alters how the action is basically serialized into text.
Walk us through what that actually looks like in the training data.
Imagine the underlying latent decision is to use a search tool. The PPA system will generate multiple views of that exact same decision. One view might format the tool call using standard JSON brackets.
Very.
Right. Another view might format it using a React-style text output. React stands for reasoning and acting, where the model is required to output a textual thought process like, thought, I need to search the database, followed by the actual action.
Okay, so it looks very different visually.
Completely different. PPA will even use tool renamings. It will take a tool originally called Finducerid and rename it in the system prompt to lookup customer.
So the AI is looking at the same underlying strategy, finding the user, but the surface-level text is completely scrambled.
By constantly shifting the formatting, the JSON, the React traces, the variable names, across all these positive and negative examples, the AI learns that the superficial text is irrelevant.
It has to look deeper.
Yeah, the math forces the preference gradient to align purely with the underlying intent of the action.
Okay, so that handles the formatting. What about the second type of PPA?
The second type is state context rewrites, and this is how they teach the AI to recover from failure.
Which goes back to the brittleness we talked about at the start.
Exactly. Instead of changing the formatting of the action, this changes the conversational history that leads up to the action. The system will artificially inject an earlier simulated mistake, along with the error message it generated, into the conversation history, right before the current step.
Ah, so it fabricates a fake backstory where the AI messed up 2 minutes ago, but it still demands the correct next move.
It places the agent in a state of local recovery. The required expert action for the current step hasn't changed, but the context window now includes the distraction of a past failure.
So it's learning to stay on track.
Right, the AI learns that it cannot just blindly follow a memorized sequence. It has to actually analyze the current state, ignore the resolved error in the history, and execute the correct latent policy.
That's brilliant. Between the action rendering rewrites stripping away the formatting bias and the state context rewrites teaching it error recovery, the Agentic-DPO process just becomes incredibly robust.
It's a very solid training regimen.
Okay, so we've thoroughly explored the mechanics now. We understand how Agentic-DPO targets the AI's highest probability mistakes offline and how PPA ensures the AI actually learns the strategy instead of just memorizing the syntax.
The theory is sound.
But theoretical elegance doesn't always translate to real-world performance. We need to see what happens when they actually test this methodology against the current standards.
And if we connect this to the bigger picture, the benchmark results are exactly why this paper is turning heads.
Let's hear the numbers.
The researchers evaluated Agentic-DPO across 3 rigorous benchmarks, each testing a different facet of agent behavior. They used Stable Toolbench for controlled API tool use. They used Mind2Web, which tests web GUI grounding, meaning the AI's ability to actually parse HTML, click buttons, and type into text boxes on live websites.
Which is super messy.
Very messy. And most importantly, they used Tailbench Retail.
Tailbench Retail, that is kind of the true test of long horizon user interleaved interaction, right?
It is notoriously difficult. It simulates real-world retail customer service environments.
So dealing with angry customers.
Basically, the AI has to talk to a user, query a database to check inventory, maybe update a shipping address, and then pivot when the user changes their mind halfway through.
Wow.
And errors in these tasks compound rapidly. A tiny formatting mistake at step 3 means the database query fails at step 4, and the entire task collapses.
So how did Agentic-DPO perform on these long horizon tasks? Let's get to the results.
So the researchers applied this training to a 9 billion parameter model. In the landscape of large language models, 9B is remarkably small and efficient.
Something you could run much cheaper than massive models like GPT-4.
Exactly. When trained with standard supervised fine-tuning, that 9B model achieved a success rate of just 21.7% on Tailbench Retail.
Yikes. Which means it fails nearly 80% of the time. I mean, if you deploy an agent that fails 4 out of 5 times in a customer service setting, your business is going to grind to a halt.
It is functionally undeployable.
Right.
But when they took that exact same 9B model and trained it using Agentic-DPO, the success rate nearly doubled, surging to 41.4%.
Going from 21 to 41% without increasing the size of the model, just by changing the training methodology.
Yes.
Now, 41% might still sound low to a human listening to this, but for a 9 billion parameter model handling complex, multi-turn enterprise tasks completely autonomously, that is a massive leap in reliability.
And to put that 41.4% in perspective, the researchers compared it to the incredibly expensive online GRPO method we discussed earlier.
The live environment one.
Right. GRPO, using full environment rollouts and live reinforcement learning, achieved a 40.0% success rate on the same model.
Wait, really?
Agentic-DPO actually slightly outperformed the live reinforcement learning method.
That is insane. And what does that mean for the compute budget? Because you said GRPO is massively expensive?
This is the metric developers care about most. Let's use standard SFT as our baseline cost, call it 1x, because Agentic-DPO only needs to run 2 forward passes locally, one for the preferred expert action and one for the generated mistake. It costs about 1.6x per step to train.
So just a little bit more than the cheapest option.
It's a little more. GRPO, on the other hand, requires multiple full trajectory rollouts in a live environment to generate a single gradient update. GRPO costs an astronomical 13.6x per step.
13.6. It is nearly 8 times cheaper than the online method, for the exact same, if not slightly better, performance.
Exactly.
You are getting the strategic reasoning of reinforcement learning at the discount price of offline training.
It's a huge win for efficiency.
What about the human cost, though? Gathering the expert trajectories, paying humans to perfectly map out thousands of workflows, is incredibly expensive. Does this method help reduce the burden of data collection?
Substantially. Because Agentic-DPO extracts a much richer learning signal from every single step, by mathematically contrasting the correct path against a highly probable mistake, it is vastly more data efficient.
And learns more from less.
Right. When tested on the stable toolbench dataset, Agentic-DPO trained on only 25% of the available expert trajectories matched the performance of older SFT methods that had been trained on 100% of the dataset.
It achieves the same mastery with a quarter of the textbook.
That's a good way to put it.
So what does this all mean? We have a method that is cheap, it's data efficient, and it doubles the success rate of small models. Have we reached the finish line for AI agent training? Or is there an inherent ceiling to a method that relies entirely on offline data?
It's a fair point, and this raises an important question about the boundaries of the technology. The paper is transparent about the fundamental limitation of Agentic-DPO.
Which is?
It is strictly bound by the expert data it is fed. It can only construct preference pairs at states that already appear in the human-provided logs.
Meaning if a scenario isn't in the expert data, the AI hasn't learned to shadowbox its mistakes against it.
Precisely. If an agent goes completely off the rails and ends up in an uncharted, deeply weird state within a software environment, something the human expert never encountered, Agentic-DPO cannot help but discover a brand new path to the goal.
It just doesn't know what to do.
Right. Online reinforcement learning, despite its cost, allows the agent to stumble around in the dark, explore novel states, and eventually find a solution on its own.
Like true trial and error.
Yes. Agentic-DPO trades that deep, unguided exploration for computational efficiency. It is designed for workflows where your expert trajectories generally cover the decision states you expect the AI to encounter.
Which frankly describes the vast majority of practical business applications. I mean, if you are automating payroll or supply chain queries, the workflows are relatively bounded. Developers will gladly trade deep exploration for an 8-fold reduction in compute costs.
Most definitely.
To bring all this together, the Johns Hopkins team has provided a masterclass in training efficiency here. They recognize that just teaching an AI to parrot human text leaves it incredibly brittle in the real world.
Which is what SFT does.
Right. By utilizing Agentic-DPO, they teach the model to mathematically contrast the expert's perfect move against its own natural highest probability mistakes. And by stabilizing that process with policy-preserving augmentation, they force the model to look past superficial formatting and learn the actual strategy of the task.
It really represents a fundamental paradigm shift away from mere imitation, moving toward true policy optimization without the prohibitive costs of live environment training.
For you listening, whether you are building the next generation of AI infrastructure or you're just a user waiting for an assistant that actually works, this research explains why the landscape is about to change.
It can move fast.
It explains why smaller, efficient 2 billion and 9 billion parameter models are suddenly going to feel vastly more resilient. They aren't just memorizing scripts anymore, they are learning the underlying policy of the tasks we give them.
They are actively learning how to identify and avoid the specific mistakes they are most likely to make.
Before we wrap up, I want to leave you with a final thought to mull over. We discussed how Agentic-DPO is currently limited by its need for pre-existing human expert trajectories to define the states. It needs that human anchor.
Right, it needs the data first.
But as these models become incredibly sophisticated at simulating their own plausible mistakes offline, could we eventually reach a point where we use a larger AI to hallucinate entirely new, completely valid environments and complex state histories?
Ah, that is a fascinating extrapolation. Using the AI to artificially generate the very states it then uses to optimize its own policy, bypassing human data collection entirely.
Effectively breaking free from the need for human-generated expert data altogether. If the models can simulate the mistake offline, maybe soon they can simulate the entire world the mistake happens in, training themselves in infinite hallucinated scenarios.
It's definitely a possibility for the future.
Something to think about the next time you ask your digital assistant to rebook a flight and it seamlessly navigates a website update without breaking a sweat. Thanks for joining us on this deep dive into the Johns Hopkins research and the future of AI agents. Until next time.